All right, welcome back everyone. My name is Jabril Bensedrin. I'm hosting this webinar on behalf of CESA Systems. Our guest speaker today is Michel Baudin, the author of 4 books on manufacturing. He comes with a very rich experience, both as an engineer in industrial companies, as a book author, and as a consultant to a number of companies that you see listed here, and I'm sure you've heard of. He has coached factories through all phases of lean implementation, and also has taught in prestigious universities, both in the US and internationally, courses ranging from assembly line design to human-machine system design, logistics and supply chain management, etc. He holds a bachelor in mathematics, master degree in engineering. He's done graduate work in Tokyo and has apprenticed for 8 years with Kei Abe. Not sure I'm pronouncing this well, but still pretty impressive. Thank you so much for being with us today, Michel, and all of you. Just a few words about our sponsor, CESA Systems. The really specificity of CESA Systems is to provide almost everything under one roof in terms of equipment and accessories that you need to implement your lean and continuous improvement. 2,500 products used by actually today more than 15,000 companies. Most of the largest companies as well as many smaller ones, with product lines ranging from training games, office furniture, ergonomics, lean office, workshop furniture, such as workbenches, quality control stations, TPM stations, computer protection equipment. In logistics, gravity flow racks, trolleys, including electric ergonomic trolleys, Kanban systems, Heijuka systems. In the visual management, also floor markings, safety signage. In Industry 4.0, digital screens, digital visual management software, digital KPI management software, wireless end-on lights, and the traditional but still very useful, essential magnetic whiteboards and magnetic accessories. That's all as far as I'm concerned. I will now pass it on to you, Michel. Again, thank you for being with us.
So first, I'd like to thank Jabril for inviting me to talk about my books. And afterwards, if you're interested in checking out what I have written lately, please visit my blog at michelbaudin.com and do not hesitate to post comments or ask questions. So I was born and raised in France and grew up wanting to become a writer. However, this required having an experience, and for that, I became an engineer and traveled quite extensively. I have now lived most of my life in the US, but I have also spent a few years in Japan and Germany and traveled to many other countries on consulting assignments. I first got involved with factories in Japan in 1980, where I first heard of the Toyota production system. Then I started out working as an engineer in Silicon Valley and then became a consultant in 1987. So the pictures you see here show me as a student in the 70s, a lecturer on lean manufacturing 20 years later, and a consultant on the shop floor in the 2000s in an auto parts plant. Along the way, I have distilled the work I've done in manufacturing 4 books covering production planning and scheduling, assembly line design and operations, logistics and supply chain management, and processes that involve human-machine interactions. And these books were intended for professionals. Now, I'm trying to share with the next generation, and I have teamed up with Professor Torbjörn Netland at ETH Zurich to co-author a textbook on introduction to manufacturing, and it's from a industrial engineering and management perspective. And we have been working on it since 2017 and expect to finish it this year. It should be available through Routledge in early 2021. My first book came out in 1990, and at that time there were a number of companies that were developing advanced planning and scheduling systems. I'm thinking of companies like i2 or Red Pepper Software, and they were the ones who found this book most useful. It was called Manufacturing Systems Analysis, and the idea was to compare various approaches like ERP, theory of constraints, and the Kanban system by applying the same analytical tools. IT has improved quite a bit over the past 30 years, much more than it has in manufacturing, where frankly it has yet to deliver on its promise. To check out the state of the art, I went last year on Christoph Roser's Van Full of Nerds tour of Industry 4.0 in Germany, and posted updates on my blog about topics like smart floors, advances in pick-to-lights, PLCs, and cobots on my blog. So this was a no, after this book came out, I changed to from working on software from manufacturing to working on the actual production floor, and had a number of consulting projects in the design and improvement of assembly operations in automotive, electronics, aerospace, and other fields, and that led to the publication of this book in 2002. The pre-existing literature on assembly was actually very limited, and it was either specific to car assembly or very abstract, math at the master's level in OR. My book addressed the generic issues of assembly, from oil tankers to toys, in a language that assembly managers and engineers could relate to. And 18 years on, most of this book is still current, even though assembly methods and technology have evolved. Toyota, for example, has migrated towards much more extensive use of kitting than I was discussing at that time. As I was doing this work, questions came up in projects about things like truck loading, less than truckload, full truckload, supplier milk runs, supplier support issues. And all of this led me to use the term lean logistics to designate all of these peripheral operations, all these routine operations of manufacturing, except the actual production of goods. Okay. That includes physical distribution, the information system, and the management practices, particularly the practice of working with suppliers. So contrary to assembly, this was the subject of an abundant literature. But under similar titles, you found books that covered only one aspect of the subject. The key point in lean logistics is that it's a system. If you use, for example, if you use small trains to deliver parts to an assembly line every 25 minutes, you need to consider jointly the hardware of tuggers and carts and the information system that tell handlers what to load and where to deliver it. Since the book came out, the use of third-party logistics has grown, and the information systems have grown more sophisticated. Not sophisticated enough, however, to deal with worldwide disruption from COVID-19. So after this, after lean logistics, I returned to production line design and operation issues with working with machines in 2007, this time focusing on processes that involve human-machine interaction. And you find those in fabrication, machining, and automated assembly. This is another subject that is not covered systematically in the literature, yet is key to the future of manufacturing, particularly in advanced economies. So I'm going to go back through each of these books and give you some examples of the sort of things that are covered in them. So in manufacturing systems analysis, about 2 years ago, a client asked me to evaluate the applicability of demand-driven MRP to their operations, which was pretty much the kind of subject matter that was within the space covered in this book. Many team members at this client were unclear about the differences between the various generations of systems their company had used over decades. So to explain these differences, I dusted up some tools from my first book and used them to map these differences. So I'm going to show you very briefly how I use these tools to show how you went from MRP through closed loop MRP, MRP2, and ERP. In 2020, suppliers still sell ERP, though that term has been used for 20 years. But the main difference between now and 20 years ago is that it's cloud-based rather than on-premises. Otherwise, functionally, they're not advertising having done anything much different. So MRP, when it started, it was just doing a time phase bill of materials explosion to calculate material requirements over time to meet a master schedule. And so this is shown here in terms of information flows. The basic logic is still used, unchanged, in today's ERP system, and its shortcomings are actually what drove Carol Tack and Chad Smith to develop demand-driven MRP. And so this basic original block is still there. So if we just combine all of this into one single bubble, we see what was added in the 70s in red here, and that was the first attempt to connect with the shop floor and track shop floor activity, and also include production planning, so that the master schedule was now generated within the system instead of an input to it. So that was the 1970s. Then in the 1980s, if we again collapse that into one single bubble, we have what was added in the MRP2 world when they changed the meaning of MRP to manufacturing resource planning. And you can see, for example, that's the first time that a function was added to extract data from these systems for people to use in their own spreadsheets or other systems. And when you go to the next generation of ERP, again, you collapse all MRP2 into one single bubble, and you see all in red here, everything that was added to it. So that was what I used to show them what all these different generations were. And it's somewhat, I mean, it looks like the classical bubble and arrow chart that you see everywhere, but it turns out that it takes quite a lot of time to generate it when you're careful about labeling the different functions and the different flows of information that take place. So again, this is an example of the kind of tool I was using in manufacturing systems analysis. What's happened in the past 30 years since this book came out? 30 years ago, the worlds of IT and manufacturing were disconnected. Essentially, you had IT experts who knew nothing about manufacturing, and manufacturing experts who knew nothing about IT. Guess what? The disconnect is still there. You still have that same disconnection. The world of manufacturing has changed, but much less than that of IT. All engineers in manufacturing, for example, have powerful laptop computers with which they could apply data science, but they don't know how to do it. Master data management is now understood to be a topic, but manufacturers went into it because they were pushed when they needed ISO 9000 certification. They didn't do it because they felt there was a functional need for it, even though that is real. DDMRP, demand-driven MRP, is an attempt to modernize the MRP core of ERP systems, and it contains some interesting ideas. Okay. And now Industry 4.0. Now that's another big topic, and I'll touch on it in the discussion of some of the other books, because it doesn't just affect the information systems. So going on to assembly, after moving from working on software for manufacturing to working directly on manufacturing improvement, I got involved with many projects that included a component of assembly. There were projects in car industry, auto parts, defense electronics, computers, laser printers, processed foods, medical devices, aircraft, agricultural machinery. It took 12 years before my first and second book. which is quite long. Lean assembly came out in 2002 with a different publisher, with Productivity Press. And in general, as you see on the left side, like assembling IKEA furniture at home, assembly is about putting things together. But in manufacturing, assembly is about making money from putting things together, which is quite a different challenge. And assembly is almost always assembly and test, because the manufacturer stands behind the products and must establish confidence that the products going out can be trusted. As a result, some inspection and final test is almost always involved. And the lean literature dismisses these activities as, quote, non-value added, but it's truly not avoidable. And so the lean assembly actually covers that topic. So what were the pre-existing conditions when I started writing this book? The assembly line design book by Wei-Min Chow is an example of the OR approach to it. It's got a lot of math, and math that is not that easy to follow, and it's essentially not the kind of coverage, not the kind of discussion that people I knew in factories are either inclined to follow. The other book that you see listed here, Industrial Assembly, is much too specific to automotive, as if nothing ever were assembled except cars. On the other hand, in Japan, I found an abundant literature that really matched what I was looking for. It addressed the audience I was writing for: production supervisors and engineers working to improve assembly lines. It consisted mostly of cartoonish infographics meant for readers who had grown up reading manga and to be read while commuting by train. And so I could have adopted this style, but I chose not to. So the book covers topics that range from the strategic, like figuring out which products are you going to assign to which production line, to the tactical, which is detailed assembly station design. Let me give you an example of a tactical issue that I didn't find covered in the pre-existing literature. Many assembly steps involve curing operations for glue, sealants, paints, varnishes, etc. The most common designs are tunnel ovens and shuttle ovens. In a tunnel oven, parts coming in at one side go out on the other side, and that physically separate the upstream and downstream operation, which breaks the continuity of the assembly line. The shuttle ovens, the problem with shuttle ovens, they're last in, first out devices, so they shuffle the process sequence. And maintaining first in, first out throughout an assembly process is essential for quality management. If you have to trace problems, it's very important to know that the products will process in the same sequence throughout the process. So one solution, which is the third picture you see here, is a tunnel oven with a return conveyor attached to its side. It allows it returns the part next to the entrance so that it doesn't break the continuity of the line, and it respects first in, first out. And so this is a concept here, and this is, as you see a picture here of that concept being implemented in an avionics supplier to Boeing in Seattle. So that was an example of the detailed design issues covered there. 18 years later, this book has stood the test of time. The bulk of the content is still applicable. Even there are more technology advanced tools, for example, for demand characterization. In feeding parts to assembly, Toyota has increased the amount of kitting versus line side supply. Pick-to-light existed in 2002, but it was expensive. It has become more common and orders of magnitude cheaper by migrating most of the technology from pick-to-light bins to wearable devices. So it's commonly seen in factories that are showcases of Industry 4.0, but the 4.0 literature doesn't cover it. And I think it's because it's really a semi-automation technology. And here's an example of the state of the art in pick-to-light. So you see the operator wears a bracelet, and the bracelet interacts with the radio frequency ID devices, an RFID tag attached to the bin. And on the other arm, the operator has a smartphone-like device that displays the pick quantity. All of this used to be done inside the bin, which made the bins cost something like $100 a piece. With only the RFID tag on the bin and all the smarts in wearable technologies carried by the operator, the cost of the bin is down to $1. So that makes that technology much more widely usable. So that's one recent development. So while I was working on this assembly project, there were questions about trucks, warehouses, forklifts, conveyors, pull systems, supplier management, a host of topics that are beyond the design of an assembly line. So logistics, why did I use the term logistics? Originally, it's a military term, and Martin van Creveld defined that as the art of moving armies and keeping them supplied. In manufacturing, as illustrated in these pictures, logistics encompasses essentially all operations to deliver goods and services, except actually making the goods or performing the services. So logistics in manufacturing includes material flows between plants, material flows between lines within plants, information flows, funds flows between customers and suppliers. It does not include the transformation of materials. So the information side, the information side was shown in these pictures above. So in logistics, what were the pre-existing conditions? So there was an abundant literature in the English language, but the focus of the books, some books were all about physical distribution, some books were all about information systems, and others were all about supplier relations. I felt the subject needed a systems approach where you cover all the issues from the sizing of bins on the line side to the organization of collaboration with suppliers, explaining how the methods used at every level fit together. Originally, it was a 2-day course before it became a book. And one attendee in that course was a former plant manager from a large auto parts company that is well known as a lean success story. At the end of the class, he told me, all the tools you described I had been made to use in my plant, but until now, no one had ever explained to me the logic behind them. So that's exactly what I was aiming for. So there is logistics outside the plant. So in that particular perspective, the plant is a node in the network with multiple tiers of suppliers on one side and multiple tiers of customers on the other side, with actually limited visibility beyond the first tier on either side. So it's easy to write that you should know your suppliers, and your customers. But the reality of this network is that its nodes are independent business entities, and that you often do not have the power to make them share information. And so there are a number of things that you need to do in order to see beyond the first tier. That makes supplier-customer relations a game in the sense of game theory. And we'll give you an example of how the game theory perspective helps understanding the issue. If we zoom in on the plant itself, find that dock-to-dock logistics inside a plant takes up most of the space for storage of material, work in process and finished goods, transportation aisles, vehicles. All of that takes up most of the space. Production is only a tiny fraction of the space, and it takes up most of the time. Materials spend more time in the hands of the logistics organization, of the materials management organization, than they do on the production line. So contrary to the overall supply chain, the plant in an environment that is in principle entirely under management control. So that's not a game in the sense that supplier-customer relations are. And distances are in feet rather than in miles, and time between deliveries are in minutes rather than hours or days. So let's examine a couple of examples of the issues from in-plant logistics and customer-supplier relations. So assume a machining process with 2 consecutive operations performed in work centers that are 200 feet apart, with a forklift used to move work pieces from operation 1 to operation 2. Okay. To reduce transportation, management decides to bring operation 2 closer to operation 1. But the results are disappointing. The main issue is not the distance, it's having to accumulate a pallet load of work pieces to move, call in a forklift, and work off a pallet at operation 2. And it's not changed by cutting the distance in half. The real improvement is achieved when instead you eliminate the transportation step altogether. For that, you have to move the equipment for operation 2 right next to operation 1 and allow each piece coming out of operation 1 to flow straight into operation 2. It's easier said than done, but if you do, you actually achieve a real improvement in logistics by re-engineering production. Managers often think that logistics is a richer target for improvement than production because it is where materials spend 90% of their time. The root cause, however, is often in the way production is organized. Another takeaway from this example is that inside a plant, it's the number of trips that matter rather than distances. With supplier, on the other hand, distance matters. Whether a supplier is 35 or 2,000 miles away makes a difference. So, now going to the issues of the highest level issues in customer-supplier relationships is how do, for example, price negotiations go? So in the relationship between a supplier and a customer, the outcome is determined by decisions made independently by two parties. That's the definition of a game in the game theory sense, two or more parties. As the negotiations play out, they agree on a price that is somewhere between the lowest the supplier can accept and the highest the customer can afford. But it's not a zero-sum game. As the literature recommends, if you move from an adversarial to a collaborative relationship, the payoff increases for both sides. Both sides make more money. So we would expect such relationships to be the norm. In reality, it's nothing of the kind. And here is why. The payoffs are higher on both sides when they work together, but not if either one does not play along. In fact, both sides in a collaborative relationship can get a short-term advantage by betraying the other and turning adversarial. From the customer side, it means taking advantage of the information shared by the supplier to browbeat them into accepting lower prices. From the supplier side, it means taking advantage of the relationship to charge above market prices. Collaborative relationships take years to develop, but they can be destroyed very quickly by this kind of action. And so it's really not a stable situation, and you really have to keep working on it to sustain it. And I'm going to mention a couple of examples from 20 years ago that illustrate both cases, both situations actually happening. Okay. The people you see on this picture on the left side, the man on the left side is Jose Ignacio Lopez, who was the head of purchasing for GM in the early 1990s. GM had been working on collaborative relationship with suppliers that Lopez leveraged to extort price concessions from suppliers. And it was so brutal and so upsetting to the supplier that some of them actually stopped doing business with GM because of it. The man on the right is Carlos Ghosn, who became the top manager at Nissan in 1999 when it was rescued from bankruptcy by Renault. Ghosn's team's initial assessment was that Nissan's factories were fine, but that Nissan lacked attractive products and that it was being gouged by suppliers. The Nissan supply chain was closely knit, with many suppliers run by former Nissan executives. When comparing prices paid by Nissan and Renault for similar parts, they found that Nissan paid 25% more. Ghosn's Nissan recovery plan put a stop to it, and most suppliers played along because bankrupting Nissan was not in their interest. Both Lopez and Ghosn were later in the news for reasons unrelated to their supply chain management practices. So 15 years on, what has happened? Third-party logistics has grown quite a bit. It's considerably more common than it used to be. Warehouse automation has grown, particularly Kiva robots at Amazon, which is not a manufacturing company, and even the Kiva robots, if you look at closely the way they work, they have not eliminated the need for human intervention. So the fully automated warehouse is still not a common sight. The concept of consolidation center has become more widely used. Most of the time, consolidation centers aggregate the input from a local cluster of suppliers for long-distance delivery to a plant. Sometimes they're also set up near a plant to receive materials from remote suppliers and act as local suppliers to the plant. So in terms of what updates we did and what we saw during the Van Full of Nerds visits, this video shows an experimental system developed at Bosch that aimed to put all the electronics of driving robots, including the robot power supplies, under the floor, so that there is no wired connection between the robots and anything else. As of 2019, it was a demonstration that you could see at the Arena 2036 research facility in Stuttgart in Germany. The man you see seated on the left here is Christoph Roser, who organized these visits. You see how the floor lights up in the neighborhood of the robot. It lights up in different colors depending on what the robot is doing. So it's quite a spectacular video, but it's only a demonstration, and it's not clear that it's actually something practical. For example, you wonder in an actual use how long the floors that are plexiglass tiles would last, and also accessing electronics that are under the floor is a problem also. After lean logistics came out, I turned my attention back to engineering, production engineering issues, but this time about processes that involve interactions between humans and machines, and that's quite a broad topic. Lean assembly was mostly about manual work in assembly. Assembly, machining, fabrication all frequently involves machines, but rarely machines that are completely unattended. The lights out factory is still science fiction. Even the most automated production lines still rely on humans to program them, start them up, shut them down, and troubleshoot them. The Toyota concept of jidoka is commonly reduced in the literature to the idea of machines that stop by themselves when they malfunction. It's really more than that. The word itself is a subtle and untranslatable pun because it's based on two Chinese characters that are pronounced the same way in Japanese. The Japanese word for automation in general means transformation into something that moves by itself, and it's pronounced jidoka. If you attach the radical for human to the kanji for move, you get the kanji for work, and it's pronounced the same. So the Toyota word means transformation into something that works by itself. So it can be unpacked at different levels. It means automation because of the way it sounds. Okay? It also means smart automation because it refers to work and not just motion. And it involves the human element as reflected in the added radical. So jidoka is, again, just a much broader subject than just machines that stop by themselves. So what are the pre-existing conditions in this particular space? The American literature on automation that I reviewed at the time ignored people. It showed diagrams and photographs of machines and light with no human in sight, except possibly to indicate scale. In the design of everyday things, Don Norman addressed human interactions for household appliances and puts forward a number of design principles to make it easy for people to figure out how to use these appliances without reading a manual and without making mistakes. These principles are highly relevant to production machinery, but they have not been applied anywhere to the same level in this field. And I've been wondering why, but I think perhaps it's because unlike household appliances, production machines are not bought by the people who use them. Then other interesting work by NASA researcher Asaf Degani expanded on Norman's concept and applied those to designing airliner cockpits with the goal of preventing pilot errors that cause 60% of airliner crashes. And he published his findings in obtaining how. And so this is pretty much the background, that the pre-existing condition to before I wrote this book. Okay. Classical automation is, this is typical of a picture where you don't see, there's no human inside here. It's a clutch assembly system, but there's nobody there. On the other hand, what you see on the right side is completely different philosophy. It's incremental automation. It's the device on the right, at the press of a foot pedal, dispenses the right amount of two compounds in an epoxy glue so that the operator does not have to worry about dosing. So it's just a small retrofit, a small semi-automatic system that makes life easier for an operator. Okay. So you put a lot of these together, you apply this kind of ingenuity to a production cell like the one in the picture. Then you have a cell where operators load parts into automatic machines that automatically eject them when done. The operators validate each part before passing it on. And further improvements gradually reduce the number of operators needed to make it run until it's eventually fully automatic. The organization then takes everything that was learned in the effort of gradually, incrementally automating this line to the design of the next one. So 13 years later, many things have happened, and of course, the most spectacular one is the most important one, I believe, is additive manufacturing, which has emerged as a revolutionary technology to make products in new and different ways. The picture you see here is of 60 3D printers that were installed on March 31st overnight at a Paris hospital to make personal protective equipment for health workers at the peak of the COVID-19 outbreak. This is a game changer and challenges production line designers to make effective use of it. What I'm currently working on is this textbook for university students of industrial engineering or operations management. It's in collaboration with Torbjörn Netland. We have taken my previous books, updated them, incorporated concepts for Torbjörn's own work, and organized the material for use in an academic environment. Students need to be introduced from scratch to concepts that manufacturing professionals are all familiar with, like even something like as simple as WIP. And the chapters need to be organized with stop and think boxes and review questions and exercises as befits a textbook. We expect to complete it by the end of this year. So thank you for your attention. I hope you find these books useful. There are many other topics on which I have accumulated material that I would like to share in new books. The Deming Legacy is a review of Deming's 14 points, 35 years after he published them. Manufacturing Data Science is about applying modern data science to help manufacturing leaders find simple answers to simple questions about their business that are still hard to find. Using videos to improve operation, that's very tactical, and the title explains what the title says it all. It's about what you need to do to make video recordings of operations, where you set the camera, what you look for, how you analyze the video once you have it, and how you improve operations through it. So again, that gives you an overview of what I've been doing. And with that, I'd like to pass the microphone back to Jabril.
Great, thank you, Michel, again for this excellent presentation. So it's time to say goodbye. Just before, a few words and reminders. This presentation is part of the CESA Systems Academy, which is both a physical site where continuous improvement, operational excellence, production teams can come and test how they can use very large range of equipment to implement their continuous improvement projects. We also have an online extension, which this webinar is part of. We have available for you a catalog which can be mailed to you in paper if you'd like to have it on your desk. It's a great catalog. I mean, I personally love it. Maybe I'm a bit biased, but I think you'll find it very useful as a resource, and it can also be sent as a PDF. Please feel free to request it. I'm happy to send it to you. You can email me. You can contact our speaker, Michel Baudin, either on his website, which actually includes his blog, and it's an amazing blog, highly recommended, and on his LinkedIn profile, which you see here. Also, I would like to encourage you to join our LinkedIn group. We have now more than 1,800, it says here 14, but we're growing pretty nicely. Engineers, peers of yours, we share content there, no spam, mostly webinar announcements, webinar recordings. To join, just go to LinkedIn, add /groups/8605844, and I'll be sure to accept you as a member. One last thing, if you'd like to receive a continuous improvement, continuous education, or I should say a professional development hour certificate, PDH certificate, please email me at jbensedrin@cesasystems.us. You'll receive a brief assessment and then your certificate. Thank you again, everyone. I hope to see you on the LinkedIn group and on a future webinar. Keep in touch. Bye-bye.